In this video, I'll do an example adding an entry into the Tetracorder expert system. During the Trex Fall rover campaign, we obtained spectra with ASD and FTIR spectrometers and UV spectrometers and performed Tetracorder analyses. One of the strange things we found is shown over here. This is FTIR, an adjuvant FTIR field spectrometer, and Tetracorder found in group 10 hydrogen peroxide. And we know hydrogen peroxide isn't stable on the Earth's surface out in baking sun. So what was causing that? My intuition during the time was this was trace carbonate. So that implies that we had carbonates, calcite and dolomite, in the expert system, but only pure calcite and dolomite. We needed trace calcite and dolomite, which had weaker bands, which have a different shape. At these longer wavelengths, the absorption bands are so strong, they change quite a bit with both grain size and abundance. In the pure mineral with normal size grain size of few to tens of microns, the absorption bands are very saturated. When they're in trace amounts, those absorption bands become unsaturated. And I'm going to show you that this idea isn't going to solve this problem, but we'll go through how we choose and why. So I've set up a directory over here, and I'm going to start specpr. We're going to assign the spectral libraries. So we have a new restart file. This is a repeat of what we did in the Tetracorder, the specpr introduction in video 2. So we need to assign the spectral libraries. So the spectral libraries are located in SL1/USGS. I'm going to press tab here to see what the options are. We want to look at the convolved spectral library. The native spectral library has a lot of different wavelengths and Viz near IR plus different wavelength regions, and a convolved spectral library makes it easier to go through and see just the spectra that are relevant to this this problem, and all at the same wavelength sampling and everything. So it makes searching through data a bit easier. So we'll go to the convolved spectral library, and it'll be an S06. And I know, to make it easy, I know that the adjuvant spectral library is AN21. So that's the spectral library. We'll come up to this other window, assign it to V, and it found it. That's good. Now let's go and find the, let's see, this one. The research spectral library, R06AN. No, excuse me. AN is Avris NextGen. We want AG, so we've got to find AG. So we'll assign U to AG, and we have to reassign this one. So we want this file, not the AN file. So that's simply that. it'll reassign it. And now we have AG21 here and AG21 here. We're done here. In the setup, we'll have to give it a name, so just copy the name. It checks the file sizes and sets the protections to read only, and that's fine. Okay, so we're basically set up. I'm going to exit and restart with I'll do my alias. So we're going to restart with this command, the restart file, graphics terminal size 2, and skip the intro. Okay, so now we're set up. We can look at spectra. Now, to make this video a little easier, I've set up some notes here. Oops. So we'll go to the display routine. The hydrogen peroxide spectrum is in the research library at U and the capital U 6. We need to change to wavelengths, auto scale. I'm going to change to line type 1. Then since we're looking at this feature over here, so let's only look at wavelength range 3.2 to 4.3. I didn't get into the change scale routine. W 3.2 to 4.3 auto scale. Okay, so there's the feature. Now, if we look up view is editing without changes, the expert system, and we're in the latest one is here. And we want the latest set up there. And then let's look for peroxide. Okay, remember when we looked at that result from the field data, it was group 10 that was identified. So this is what was identified. And so we want to plot the parameters for this this feature, but this is curve continua. So we can't do curve continuum yet in for the Tetracorder continuum in SpecPR, but we can look at the center wavelengths and do a linear continuum. So I just took this part and the center 4 wavelengths, that's the left and right continua, and changed the C to a capital L, and I did that down here. So you see that the C was changed to L, and then the center 4 wavelengths. So if we run this command, somehow need to get out of that mode that we're in, auto scale, then execute this command, and we have, this is the wavelengths that are used for the for identifying this feature. Now, the, the suspicion was that this feature was due to a carbonate in now this is hydrogen peroxide, but I thought that carbonate would have a similar band position. So I defined a bunch of wavelength markers here, and I'm just going to run these through. So the red position you can see over here is calcite, and the dark blue over here is calcite. The lighter orange, or the orange, is dolomite. The cyan is dolomite, and then the green is the hydrogen peroxide position. So if we plot a a, um, a calcite with trace amount of calcite, will it match this feature? So I have made some other notes here. And the first thing to look at is the full calcite. Let's see, let's look at the dolomite. It'll be a good example. So first, and I forgot to do one other thing. To keep the hydrogen peroxide spectrum on with any plot we do, we make it an overlay. So I'm doing this. So now we see that overlay 1 will be a red line, and this is the hydrogen peroxide spectrum. So now we go back down. Dolomite is that would be V, and we'll do an auto scale. So this is a dolomite spectrum, and here's the continuum. This is the hydrogen peroxide continuum. So we can see that dolomite will not fit the hydrogen peroxide spectrum. So an idea that this 3.5 feature in the field data was due to dolomite is wrong. So is it due to calcite? See, the band position is shifted longer and closer to the peroxide position. But we'll try this one. Here's a weak calcite. You can see these absorptions are pretty strong, and and even this is a weak feature. It's not pure calcite spectrum because it's dolomite in an antigerite sample. So let's go out and plot a weak calcite feature. And we see it too doesn't work for this kind of broad feature. So the idea that it was a carbonate threw me. And so I spent some time, and I'm not going to do that too much here. I'll do an example. So we don't need this. I'm also in, actually I need to go up to my test directory that I'm working in. So now all three windows here are in the same directory. And I made listings of the spectral libraries here, so I'd have them for my reference, and I could even take notes or edit it and take notes in them or put notes in them. So I could edit it with changes if I wanted to. So let's look for we can go through and check all kinds of spectra pretty quickly. We'll start when it has 3 letters, that's an IR spectrum. These others are Vis near IR. So let's start at record 48. So V48, we're going to look at all kinds of spectra, and we'll auto scale each one so it fits on the plot and can compare this feature or whatever shows up in the spectra to the hydrogen peroxide spectrum. And you can watch actinolite, you can watch the name up here. So we can go through these pretty quick. When nothing is shown on, there's no data. It's probably an ASD spectrum, which doesn't include the longer wavelengths. And I'm just typing E return, and it pages through the spectra. So I can go through and see what works and what doesn't. So I did that I went through the entire library. Took a while. You can see most of these spectra, let me get to one of these. These are trace organics in the sample. So this almandine has trace organics. This is probably a few tens of parts per million. So after going through them, I found a couple of possibilities. Let's go to 372. Well, let's go to 378. So uh, this is an ammonium illite, and it has a broad feature very similar. After looking at a number of ammonium compounds, then it seems like that what we thought, what this was matching in the Tetracorder expert system wasn't hydrogen peroxide, it was ammonium compounds. I mean, think about it, fertilizer and animals out there, there likely could be ammonium products in the soils. So let's, I had marked a few down here. I guess I didn't put in as many as I thought I did. Oh, yeah, here we go, these. Okay, let's look at this one. So that other one was shifted a little bit longer. This one's shifted a bit shorter. And since we only have one of these in, one feature like this, anything that's close will probably match. And now let's look at this other one. And that has a band that's basically right on. So in a continuum removed feature, and in fact, we can now do that. You see the absorption bands are very close. So let's add this one. So it's a budding tonite. A budding tonite is an ammonium-bearing feldspar, but it's a proxy. Anything with ammonia in it and an ammonium ion will have similar absorption bands. So this feature isn't necessarily a diagnostic identification of budding tonite, but a diagnostic identification of an ammonium ion. Okay, so we have our target. Now we need to go to the best thing to do is to be careful not to upset the current thing. So I'm going to copy this this expert system because we don't want to modify it to, we can call it something new. And we want to search for peroxide, because our setup is going to be pretty similar. So if we look at here to here, copy that, and I'm just going to quit. And I'm going to and this would be budding tonight. Okay, so now we can take this short piece. Be sure and not leave blank lines like that. So first thing to decide on, maybe down here, is what we're going to call it, because we want to be sure. So like this sample is budding tonight, but it's not diagnostic of budding tonight. So the idea that we do is we call it something like ammonium dash, and this is actually a budding tonight montmorillonite. That's what the mont is here. We could leave that off completely, or if we're putting in a number of ammonium compounds, it's a good idea to make it a unique so that we can identify the reference material just by looking at the file name on an output file. So and then let's look at the band position. So we didn't quite get that yet. So it's again 3.526. 3.52 is close enough. Oops. Okay, so we have that. Then let's come up here and change the ID to something like that. Then we have our we're using 5502, so that's this one. So we need to change the record number to 5502. Then we change this comment title to the title that's in the library. And then we have an output title. So now we need to decide, the only other thing we must do for sure is, of course, we could decide on things like how we scale the output DN in an image, if we need other actions, what our thresholds are, and our wavelength continuum intervals. So probably most important, let me move this down a little bit and move it over here so we can see things a little better. Okay, so our continuum interval, it looks okay right here. I like those. They're not much different than these. So then for the curved continuum, if we look at, we do a capital G and we can read the graphics cursor positions, and we can make this a little smaller. So that's the 3.42, and that's 3.4 to 3.44. So 3.42 is right in between, and then around 3.7, and that's 3.7. Okay, so that looks good. So now the other one, 3.83 to 3.87, so about 3.85. So that's right about in there. And if I'm drawing a continuum, yeah, that would be something like I would do. And then the shorter wavelength, 3.278, so around 3.31 or so. uh, 3.31, somewhere in there. That looks reasonable. So these continuum points, while they worked for peroxide, they also work for this ammonium sample. So we can go with that. Um, these kind of things are pretty generic, and unless the sample is extremely dark, so continuum threshold of 0.02, 2% reflectance, and we see out here um, we have 15% reflectance for these this spectrum, so that's quite reasonable. We'd have to look up what the this is the reflectance times the band depth has to be greater than what this is, and we don't have that here. We'd have to go and look it up in the original expert system, but that value's been working, so we'll keep it for this feature also. So with that, we're done, and now we can drop that in to the expert system, and we can do that. So we have this Buddingtonite entry, and we have this entry here. So let's edit this, and I'm going to put this copy of this file name into the copy buffer. So we're right here with the hydrogen peroxides. We can now add this in at the end. Actually, NVI, we do it a little differently. So there's the new entry, and we don't need a double comment there. One's fine. So we can double check. Ammonium Buddingtonite, ammonium, looks good, looks good. Output. So we're good there. This looks good enough now. Now that we've made a new entry into the Tetracorder expert system, we need to test it. So in this case, we added a single entry to add an ammonium compound for mapping in the 3.5 micron region. We don't have an imaging spectroscopy image cube that covers that wavelength region for the Earth, so we'll use a single spectrum to do the testing. So I am in a directory here, and we had previously been running Tetracorder in this directory, and we're going to create a new directory to run Tetracorder in a single spectrum mode. You can always read the README files and setup in the current directory. So 5.26e is our most current directory. And down here is single spectrum analysis. You can read through this and get more details. So we are in this directory. We're going to run Tetracorder, but 5.2a is not the most current. So it's really 5.26e commands, and then the command to set up a tetracorder run is command-setup-tet run. And if you don't know what the options are, press return and it'll tell you. So in this case, we need a subdirectory, and we were going to use a directory similar but different than the current directory. Our data set is Agilent FTIR. That's over here. So we copy that. Then we need, after dataset, single spectrum. We're not going to follow a growing file, so no follow. Minus T for temperature, minus 10 to 30 centigrade. Pressure, bar, and that's all we need. So if we press return, and notice that I'll need to update this README file. It's a little bit out of date because it doesn't have the minus T and the minus P, so it's a little bit older command. So confirm that what's being directed in the README file is current. At least this gives you an idea on where to look. So we don't need that at the moment. And we can do this setup here. And it didn't like one thing, so what did I miss? I missed, it made the directory. Oh, it needed a capital C. Okay, so that's easy to correct. It made the directory, which we have to remove. So we'll start over here. Capital C. Good, now it worked. CD. Well, actually, we're going to do we can do the run right here. Before we actually do the Tetracorder run, the restart file doesn't have the test spec.pr file that we need. The test spec.pr file is here, which is from this subdirectory is up one directory. So we need to add this to the restart file. We can do this by starting spec.pr. You see that there's nothing assigned to the letter V, so let's go and reassign letter V. Okay, that looks good. Change the name of V. Done. Set the protection. Now we're all set up and ready to go. Let's list V so we know which spectrum we want to look at. So the spectrum was this one here that identified hydrogen peroxide, so it's V30. So now we're all set to run Tetracorder. We can exit spec.pr. We can start Tetracorder here like this. We have to read in the expert system. We do that here. Okay, now we're set. There's a lot of information here, but we're going to do type S to analyze a single spectrum. It wants the file ID and record numbers. That's V30. There are some options to include. We don't need to do anything here. Thresholds, we don't need any thresholds. We can have a full diagnostic. Let's try just the one-line answers. We don't need a comment. Test 1. And we still got hydrogen peroxide. So why is hydrogen peroxide a better fit than ammonium? Well, to look at it in more detail, let's run it again. Single spectrum, oops, V30. Let's do 3 as full diagnostic output. So this goes on forever. We'd have to go back a long ways and look for all the entries. And what would be best to do would be to copy this to a this is the final answers, but we can copy this to a file. I did a middle button paste. It'll show up here in a second. Write that file. Now let's look for so here's our hydrogen peroxide. So the fit was 0.68 versus 0.67. So the hydrogen peroxide still had a slightly better fit. What this is telling us is that these two are very close and very hard to tell apart, and maybe a different ammonium compound would do better. It's interesting that they both have such similar bands. So the question is, what other examples ammonium compounds do we need, or do we need yet another ammonium compound, not a mineral, which is the only thing we have in the library? So it's a good lesson that the library needs to be complete with enough examples to map what you're doing. We probably should have obtained a sample of this and done an analysis to see what exactly was causing this absorption band, if it was really hydrogen peroxide, or if there's yet another ammonium compound, like a fertilizer, or from ammonium products from animals that get into the soil. So it needs more research to fully resolve this issue, but it gives you a good example of what we're up against when we're pushing new boundaries, and this 3.5 micron region is such a new boundary. An addendum, because we didn't change the Tetracorder result, I looked at the ammonium compounds in more detail, and I added 2 more ammonium compounds, and I called this version RC2 down here. So here's the peroxide. I adjusted the continuous slightly because the analysis showed of the continuum showed it could have been optimized just a little bit. Then we added previously the ammonium butylenite. That's unchanged. I did fix the spelling on ammonium, and I added the more precise band position for here. I also changed the band position to be more precise on the peroxide, 3.54 microns. Then I added an ammonium illite smectite. The continuum was a little bit different, and this is at a longer wavelength, 3.56 microns. and I added an ammonium alunite jarosite, and that has a shorter band position at 3.50 microns. So the peroxide is still a different position than these three. It's at 3.54. We have 3.5, 3.56, and 3.526. 3.53 approximately. So the hydrogen peroxide is still a little bit different. These are very broad bands, but the tetracorder analysis is very sensitive to the band position. So we'll see if these new additions change anything. So I've already done the setup here. We'll do single spectrum mode, V30, and um, just the output or the final answer, and lo and behold, we still have hydrogen peroxide. Let's look at the results file. We don't need to rerun and capture. The results file always have the full output. So we'll view that, and here's the 4 entries, and we see that the hydrogen peroxide is still the best band position. The has a little bit stronger band depth. So for what we're seeing in the soils, the band position is 3.54, whereas these are not capturing that. So we probably need to add some additional ammonium compounds and make measurements of additional ammonium compounds to see if there's a common band position that explains hydrogen peroxide, or maybe there is hydrogen peroxide in the soils. So a learning experience. This is another addendum. If we look at our mapping results from our last attempt, we saw that the fits were very close on 2 of them and not too far off on yet another. But notice also that the band depths, 0.02 or 0.028, they're very weak. So one of the reasons why these fits are not 0.99 or so is because we're battling signal to noise with a very tiny band depth. And that's okay. But in either case, what we've learned is that the hydrogen peroxide 3.5 band occurs at a similar position with symmetry as ammonium bands. So let's do one more change. Because of this uncertainty, our output should not be this precise. So we're going to copy this, and again, every time we make a change, that'll change the output. We should increment the expert system file name. So we're going to edit this, find the peroxide group 10 entry, and then call this or. We could shorten these. An alternative way to make a shorter name would be H2O2 or NH4. The ID I like here, but let's change this to an H4. So at least it's similar. Okay, then, so this absorption band position is 3.54 microns. So any other position that is close to that, so this is 3.53, this should probably also be changed. And H4 or H2O2. We should probably change the output title up here also. This is getting complex. It's weird that we have hydrogen peroxide twice here. So we have these two features at 3.53, 3.54. We can look at these others. This one is at 3.56. That's shifted enough that it shouldn't be confused with um, hydrogen peroxide bands. And then this other one is at 3.50, and it's shifted enough that it also would not be confused. So with that, we're less certain on the output, and the output names will be will reflect that uncertainty. Have to spell correctly. Check our spelling up here, or yep, okay, so that's good. So we've made that change. Let's also change the setup. Okay, so now we're all set with that new command file, and if we rerun the example over here, it would reflect those new names. To further refine this, we would need to make more measurements and see what the total range of ammonium features are. Also, hydrogen peroxide, these are room temperature hydrogen peroxides and ammonium spectra. If we were working on other planets, like hydrogen peroxide is found on Europa, Jupiter's moon. So we also need at least one low temperature spectrum, and we have that. I've added that to the research library, and I'll incorporate that into a future version of the expert system. And then we would also include, let's go back up to here. We would also include a constraint on temperature. So we don't have any constraints on temperature here, but we would add a constraint for low temperature versus high temperature compounds. All of this illustrates the complexity um, in setting up the expert system. You need um, enough spectra to distinguish between the compounds, and you need to work to, when there's an anomaly that you observe in the field, work that through to see if you're mapping that correctly or if you need more entries into the spectral library. And it's pieces like this that have allowed us to grow the system over the last 30 years and refine it for working in more environments. Not all entries like this are this complicated, but I wanted to show the the total effort that can get involved with making entries. So if you start a new wavelength region, you need to know the diversity of spectral features that are going to be expressed in that region and adequately include spectra and entries in the expert system to distinguish that diversity. Thank you for listening.